Yeah, okay, so thank you for being here, and I wish to thank Giorgio and the organizer for letting me give this talk. It's a real pleasure. And so, number one is Monash University, it's the place I'm coming from. Number two is I'm here. And number three is where I'm going to be. So I'm going to be back in Italy next year. And we will see something about Strassen conjecture. So Strassen name has appeared many, many times. So he has been lingering in the room for all these 3 days. And finally, we are going to see what the conjecture is, and then Elisa is going to tell something on the conjecture from a completely different perspective. This is my understanding. It's going to be different because basically we will speak about special tensors, which are symmetric tensors, so homogeneous polynomials. So this is my idea, and this is not unfortunately. So we start with these very basic things, so multiplication of 2 by 2 matrices. Hopefully there is no mistake, so please don't check. So just look at the nice color, black, blue, magenta, and red. And if you look at it, you see that, well, we need 8 elementary operations, addition and multiplications, if we want to perform this operation. And it's
12 up there.
Well, don't look at it. I just said it before. And then there is this tensor T, which is representing the multiplication of 2 by 2 matrices. And the idea is that the first C4 dual is just selecting A's, the second one is selecting B's, and the last C4 is just a placeholder, which is telling you which element of the target matrix you are computing. So this is very natural. We know very well about this. And in tensor notation, we can just write down T, and Frank, again, please just look at the colors. So there is black, blue, and the 4 colors. Each color is representing an entry of the matrix. So you see in black is C11, blue you have C12, and so on. And you have 8 summands. So this is why we say you need 8 elementary operations. And each of these summand is what we call an elementary tensor, or it has been called also primitive tensor. Simply means is the simplest tensor you can produce because it's product of vectors, so you don't have addition involved. So this is a very basic notion, and T is written using 8 of them. And this is a very usual thing. And Strassen in 1969 basically proved that you can just use 7 elementary tensors. And if I got the story right, he basically was trying to show that 8 is optimal, and he didn't manage 2, and then he realized, I think just by good luck, that, well, you can do with 7. And how did he do this? Well, basically it's a change of basis. So you can write T using the following summands. So number 1 is just because red is the first summand. And you see that what's different from what we did before is that each of these vector you're going to compute the tensor product of are now sum of what we used before. So you perform some linear operation, and then you have a second summand, and then you keep going, and you finish with 7 summands. What is really good about this expression is that each of the 7 lines, only 3 you can see, so there is no mistake possible because you don't know what is here. So there is nothing wrong in what I wrote. And what is good is that each line is only involving 1 elementary tensor. So it's just involving 1 multiplication in some sense. And so you manage to write the same tensor we wrote before using 8, using 7 elementary tensors. And this is what I understand Strassen result to be.
Why do you call this a change of basis?
Oh, just a way for me to remember what I want to say. It's just that you change a little bit the elements you use. It's not precise. It's just an idea. Okay. It's probably not very appropriate, but just you recall me what I want to say. Okay, remind me, sorry. Okay, in modern terms, Strassen showed that the tensor rank of T is at most 7. And this was a breakthrough result at the time for basically 2 reasons. So reason number 1 is that this result allowed to the development of faster algorithm for matrix multiplication, not just 2 by 2, but n by n, by making them of even size and then splitting them in blocks. And it was really relevant in the 60s because I think that performing operation was the real obstacle. It was not easy to perform multiplication. Perform many of them was difficult, so even a little bit of saving was very good. Nowadays, I'm not an expert in computational mathematics. It looks like what everyone is concerned with is the curse of dimensionality. So you're not worried so much with computing, but with storing. So in some sense, Strassen result in this version is not really good because it requires you to pre-compute and store information and then to perform the operation. And now in computational mathematics, they prefer to compute a lot more rather than storing a lot of information. So this is why maybe this is not the biggest contribute we can draw from this result. But the second contribute is still relevant and basically was saying to people, well, even if you are considering a very straightforward algorithm, something you think you know very well, multiplying 2 by 2 matrices is easy, well, there are surprises. Maybe the computational complexity, whatever you want to denote with that, is not what you expect. So you have to be very careful when you want to decompose tensors or find optimal algorithm. Yep.
Just to comment on your first comment, Strassen actually moves less data, can be organized to move less data than standard matrix multiply.
So it can be organized because also moving data is another problem, not only storing them, but moving them between these parallel clusters things. Yeah. Okay, thank you. Okay. And so here comes the conjecture, basically in 1973, about the multiplication of 2 by 2 matrices. And in some sense, it was basically telling you, well, I have two pairs of matrices, A, B, and C, D, and I want to multiply them. And what is the best way of doing this? Is this just a trivial thing? I first multiply A times B, and then I multiply C times D, and I'm done? Or there is an interesting way of entangling the two multiplications in such a way you can save, you can perform in a better way. So basically, this is the idea I see underlying the conjecture. And if you want to be more on the philosophical side, we can say, well, you have an algorithm, and this algorithm is optimal in performing a task. You want to perform the task twice, and you ask yourself, is the best way just to apply twice the same algorithm, or there is a way to devise something better? And there is at least one nice example. I spoke with this with JM about cooking pasta. So I'm Italian, I should be able to say something about this. So if you want to cook pasta, you make the water boil. After the water is boiling, you put the salt, and then you put the pasta, you wait for the appropriate amount of time, get rid of the water, and then you have your dish of pasta. But suppose that Luke is coming to visit you, you want to cook 2 dishes of pasta. Then what you have to do, just repeat twice the same process, or maybe use more water, more salt, and then maybe if you're mixing kind of pasta, it's difficult because you have to time in a different way, but maybe this is more efficient, you save energy, maybe you save water. So it's not so immediate to understand what the best thing is. And JM is another example about changing diapers to 2 babies, something like that. And as I'm here without my wife and my daughter, I don't want to think about that just for 1 week, so I don't speak about that example too. But there are just funny examples to get you have the idea of what the problem is.
So how is this a conjecture? A conjecture is something you could decide. This is just
And this is what you can decide. From my point of view, this is the version, what I call the conjecture is in terms of tensors in independent set of variables. So you take just vector spaces, V1
I
up to
understand.
the n.
It was a question. Can you do this? A conjecture,
the question...
conjecture should be like a statement that it's either true or false.
So the conjecture, sorry. You're right. The conjecture is that you cannot do in a better way. You're perfectly right.
Okay.
Now I understand what you mean, sorry. So the conjecture is that you cannot multiply the 2 pairs in a more efficient way if you know exactly what is the best for each pair. Yeah, thanks. Now I understand what you mean. Yeah, I was distracted by the pasta cooking. But,
Getting hungry?
yeah.
Did you just have lunch?
I'm not hungry anymore. So this is the one version we can use is using tensors, so you can make it in some sense more precise. And independent set of variables means that these vector spaces do not share anything in common. And again, we use the notion of tensor rank using elementary tensors. So you have your tensor Ti, and the rank is a number, which is telling you what is the least number of tensors, elementary tensor you have to use to write it as a sum of them. And then you can look at this expression. Clearly, if you take the sum of the Ti, you can write it using as many elementary tensor as the sum of the ranks, because I can write each Ti using that many. You put all of them together, you get a long expression. This you can do. And the question is, can you do better? And so the conjecture is that you can't. So they are equal. So if the Ti's are in different set of variables, the best you can do is just a trivial thing. Decompose each summand separately, and this is the best. And this is how we phrase the conjecture, and then you can ask yourself, now that it is a conjecture, thank Frank, you can ask yourself, is it true or false? And you can make up your mind if you believe it's true or false, and since I have been working on this, I am changing each 2 weeks my opinion. Maybe it's true, maybe it's false, depending on what we manage to do. And when you find a problem, you see, well, maybe I can construct a counterexample, and then you manage to solve it, or your friend managed to do that, so then you believe it's true. So it depends if you're optimistic or pessimistic, and in life it goes up and down. But I think that in general, among experts, there is no common agreement about that, if it is false or true. So it's really open. Can be, in some sense, both of them, we don't know. It would be a surprise in any way, and it would be really nice to see how it is working. And as this is so difficult, there is also this approximated version, which in some sense we saw many, many times. And this is based on the notion of border rank. Everyone knows what it is. Basically, you want to write T as a sum of T tensors, depending on some parameter lambda. And taking the limit, you get the T you want. Without the limit, you don't. So you can do better in this way sometimes. This is what you expect. And the conjecture, in this case, is known to be false. So if you look at border ranks, the border rank of the sum can be smaller. And this is important because discovering that it can be smaller allows you to construct faster, say, more efficient algorithm, requiring less elementary operation. And there is also another version of the conjecture, which we can call the symmetric conjecture. And basically, this is based on the fact that symmetric tensors are a relevant example, and they are just homogeneous polynomials. So they are in some sense easier to treat. You have more tools, especially from commutative algebra and algebraic geometry, to deal with them. And this makes it possible to get more results. So the idea is that, well, try this version of the conjecture. If you can decide this one, then you can try and study the general one. But keep in mind that they are not the same thing, because the symmetric tensor rank and the rank are not known to be equal. Even for symmetric tensor, this is common conjecture, so it's not solving the same problem. But if you get some way of doing this, there is good hope you can try and go for the general thing. So you just introduce your forms in independent set of variables, and the Waring rank is just the symmetric tensor rank, just for historical reason, this is the way I call it. And you define it in the most natural way. Simply, you replace elementary tensor with symmetric elementary tensors, and they are just dth power of linear forms. So this is how you can define the Waring rank. And then, again, clearly the amount of powers you need to write the sum of the Fi is at most the sum of the powers you need to express each one, and you want to know if you can do better. Can you reduce the number to the right, or are they equal? And the symmetric version of Strassen conjecture is basically telling you that if you have homogeneous polynomials of degree d in independent set of variables, then the rank of the sum is the sum of the ranks. You cannot do better. So this is basically what the conjecture is telling you. And what is difficult about trying to prove this conjecture is that the Waring rank is quite difficult to compute. It's not easy, so you cannot do many examples. But the fact is also difficult to characterize it. And the thing you have to do, basically, is to characterize the Waring rank of each Fi in such a way you can use this characterization to describe the rank of F. So this is the very difficult task, is both to describe the rank of a form in a nice way and to describe the rank of a sum of forms in a way using these atomic elements you, in some sense, manage to achieve or to compute or to determine. Okay, so let's see something about the Waring rank, because this is what we're going to use, and how you can compute bounds on the Waring rank. Usually, from my point of view, it's not difficult to find upper bounds. What is really difficult is to find good lower bounds. And as far as I know, there are two approaches to do this. So one approach is due to Landsberg-Titler, 2009. And this is I think it's quite a famous paper now in the Foundation of Computational Mathematics. They had a very nice idea, a geometric idea of computer rank with a lot of consequences, and we will see that. Another approach, which I know, is due to quite a lot of people, and is a very simple idea. In some sense, the idea is coming from this paper of 2012, but it took a long while before Jung-Wu and Marvi Catalizano realized that you can use it in a much more efficient way. Basically, using the idea of 2012, we could just do some few examples, But then, especially the Korean guy, Jung, who had a very nice idea, and that is what is going to be part of this 2014 project. And now I'd like to say something more about the basic language if you want to use these techniques. From my point of view, they both use a polarity theory. Maybe JM has a different idea of what a polarity theory is, especially in 2009 it was completely different, but if you look inside it, this is what I see. So I think this is the common ground for both the two different techniques you can use. So just a brief reminder of what is a polarity theory. You start with your ring of polynomials, S, and then you introduce a new polynomial ring in new variables, y's. And the idea is that you want T to act on S in a very natural way, which is by differentiation. So each variable of the ring T I see as a differential operator. So yi is just a derivative with respect to xi. And if you take a monomial, you just take several derivatives. If you take any element in T, it's just a differential operator acting on S. And once you make these, you can attach to each polynomial, homogeneous polynomial in S, a very nice object which is called the perp ideal, which is basically the set of all differential operator killing F. And you can prove that this set is closed under addition, very easy. It's also closed under outside multiplication, so it is an ideal, and it has a very nice property. But the most important one, relating it to Waring rank and Strassen conjecture, is the so-called polarity lemma, which is telling you that you can write F as a sum of R powers of the diff power of linear forms, if and only if inside F perp you have a very special ideal, which is the ideal of a set of R points. And this basically means that you have your R points and you have all the polynomials vanishing at them, and they form this nice ideal I. And this is the condition, if and only if sufficient and necessary condition, to know if you can write F as a sum of diff powers of linear form, exactly in the number of R. And it's not easy, however, once you have F perp, to decide what is the minimal R set of cardinality of a set of points such that the ideal of the set of points is inside F perp. So it's not making your problem easier, but you can use a lot of techniques from algebraic geometry, because now you start speaking about set of points, and then you can use Weber functions and these many tools. So this is why symmetric tensors are, for me, nicer to treat, because we have all this geometrical approach set up for you and you can just play with it. So what is Landsberg-Titler approach? Well, this is my version of it, so any mistake just come from me. It's not their fault. But the basic idea is that the rank of F can be bounded by below by 1 plus the dimension of sigma s, which is just the locus of s plus 1 upol points of the hypersurface f equals 0. So if you have polynomial f, you can look at the geometrical object that it defines as the 0 locus. And for example, if s is 0, you are just looking for the points of this hypersurface. If s is 1, you are looking for singular points in which all first partial derivatives vanish. If s is 2, then you're looking for second derivatives vanishing, and so on. So this is, in some sense, the singular locus of appropriate, say, degree of f. And then the last summand is the dimension of a vector space. You take the ring T, you mod out by the ideal f perp. Everything is graded, so it's a direct sum of homogeneous pieces. You just take the S piece, look at the dimension, and that number you cook up in this way is a lower bound for the rank of f. I think it is a beautiful result, also because it's mixing the geometrical properties of f. I think it's the first time I saw anything like this, with some of this algebraic property of the polar ideal. Yep.
What is T?
Sorry?
What is T?
What is
T.
What is
Ring.
T? Oh, T is the ring of, is here. Yeah. Is the new ring with, you have differential operators. The ring polynomials in the y's, which you see as differential operators. And another question is, what is S? Well, I think that S is part of the art of the problem. You can pick S as you want. If you are not careful, you get a very small lower bound, which is useless. Then you start moving S, and the lower bound is going to increase. And maybe you are very happy because the lower bound is equal to some upper bound you have, and then you compute the Waring rank, which is always good. If you don't manage, you get a good lower bound anyway. And some application, only few of the many they had, are the following. So for example, they managed to compute the rank of these two reducible forms. Maybe a surprise, but in 2009 it was not known. And with their method is probably a one-line proof, something like that. It's just a computation. They also managed to get lower bound, not optimal, too bad for them, good for me, for monomials. And finally, which is probably, I think, the most relevant one, they managed to get lower bounds for the Waring rank of determinant and permanent of generic matrices, so matrices filled with indeterminates. And I think this is the first result about the Waring rank about them, which was new, 2009. And maybe it was improved 1 or 2 years ago by this student by Jarobino. But you see, it's probably one of the best things you can get from this because it was completely unexpected, at least from my point of view, and not easily improved. Okay, what is about this group of people working on the project? Well, you can use this other approach to find a lower bound. So basically, you don't look at the geometry of the hypersurface, you just look at the algebraic aspect, and you have a lot of freedom here. So from the other perspective, the freedom was the number S. From this perspective, the freedom is that you can choose your ideal I as you want, as soon as it is generated by linear forms. And then you can pick a linear form inside this ideal. You can perform this operation. You compute the quotient, F perp colon I plus L is a new ideal. And this is what you can choose. Once you have your new ideal, you look at this quotient, and this is a graded ring, only with finitely many non-zero homogeneous species. So you take this sum. Actually, the sum you can say for any value of I, but only from 0 to d plus 1. You have something which is not 0. You put all of these numbers together, you get a number. This is a lower bound for the Waring rank. And again, if you are not careful, yep.
What happens if...
Yeah, why d plus 1? It's already includes everything of degree d plus 1.
Well, this is for sure. After d plus 1, you get all zeros, right?
Yeah.
Yeah, so it was just a way to say you can stop there.
I think you can stop in d.
Oh, yes, but it was just to say you can stop there. There's no way you have to consider lower than 0 or bigger than d plus 1.
So
this is enough.
Just take the dimension of the quotient, that's a finite.
Yeah.
Well, I think this is in red just because I was expecting this kind of problems, and in fact, it will disappear. So from this point on, I will just say sum over all values of I and only find a number of the good ones, at most d, whatever, yep.
And what happens if you make a mistake and pick a non-general L?
Then you get a number, but that number is not clear to me what is telling you. And the reason
Which way, I mean, does it overestimate, underestimate, or there's no correlation?
So the way I see this is that L maybe is a 0 divisor, and then you cannot play that game anymore. Yeah, basically you are killing twice the same thing, yeah. So you can get a number which is too big, but it's not the good lower bound, it's false. It's too big, yeah. And again, some applications, and they are following the same line of what we did before. So you see, they are the same they did with A equal 1 and B equal 2. But actually, with this approach, you can see that you can do much more. So you can just take any A and B, but the condition is that A plus 1 has to be at least B. If it is smaller, well, this is not working. Okay? There are difficulties. If A plus 1 is less than D, we managed to do, but only with 3 variables. So this means we can compute the rank, it's a nice number. But in this situation, with more than 3 variables, we don't manage to do if A is too small. I don't know why yet, but there should be a reason. And then we also managed to compute the Waring rank of all monomials using this formula, which by luck give the lower bound, which is equal to the natural upper bound. And so you can prove that the Waring rank exactly what you want. Okay, and then monomials. I want to say something more about monomials, and you will see why. They are just an easy example, but they have something really special, which is probably not what you expect to be, not the fact that they factor. This is not what is special. There is something as special about them, and it's going to be very relevant for the Strassen conjecture aspects I want to show you. So let's start with the easy part. So what is the result about monomial is that the rank is given by this nice formula. You multiply all the exponent, increase by 1, but the smallest you can forget. you can get these computing using the previous lower bound and an upper bound, which is pretty natural. So we know the Weyl rank of monomials. But we also know that monomials in different set of variables satisfy Strassen conjecture. So this was stated about coprime monomials. Coprime means that if you take two of them and you compute the GCD is equal 1. Since monomial factor, this means no common variable. So coprime and in different set of variables is the same thing. And in that 2012 paper, we also managed to show that the rank of the sum is the sum of the ranks. And at the time, these just looked like a very peculiar property of monomials, which was not so clear where it was coming from. Now I'd like to show you what, from our point of view, is the real special property of monomials. So what is special about monomials? And the best way to see it is just to go through one example. So we compute together the Weyl rank of this monomial. So we compute the perp ideal, just increase each exponent by 1, and that's the perp ideal. And inside this f perp, it's clear that we have these ideal here. And from my point of view, so this y square 4th power minus y0 4th power is a collection of 4 distinct lines like this. And when you look at y1 cube, y0 cube, this is a collection of 3 lines like this. So you have this nice grid, and the intersection points of this grid are actually the points of the polarity lemma. So in some sense, I is defining the ideal of 12 points in this precise way. And so by the polarity lemma, you know that the rank of f is at most 12. Because you can decompose it using 12, because by the polarity lemma, you have a set of 12 points, the ideal of a set of 12 points, distinct, and then you can play this kind of game. How do you get the lower bound? Well, the lower bound you can get using the technique we showed before in a very simple case, because you don't have an ideal I of many linear forms, just one. You take the same linear form twice, you get this nice ideal, which is a complete intersection of degree 12, if you want to be sophisticated, which simply means that when you compute the sum with no upper bound and lower bound, you see, you just compute the sum, you get exactly number 12.
I don't understand the notation.
Yeah, tell me.
Y0 plus Y0 equals...
It's Y0, sir.
Y0...
It's
F divided
This
by
level?
ideal plus an ideal.
Oh, the f perp colon y0. Yeah.
Per colon
Yeah.
Y0. But
Yeah,
plus...
the parenthesis is missing. No?
Yes.
Well, it's missing, but I don't think it's really necessary here.
But
I can-
The order of operations?
I can write it here if you want.
I think I got
It's
it.
not something you don't want to do, right?
I got it now.
Okay, but that's a good question. You have f perp, colon the ideal y0, you get a larger ideal, and then you throw y0 inside, and that's what you get. Yeah, and then you use that ideal to apply the lower bound formula, and you get exactly 12. And in this case, it's very easy to see why you get 12. And it's also very easy to see why any exponent of the lowest exponent is not playing a game, because when you are at this level, the variable with the lowest exponent will have always exponent equal 1. And this is why in the formula I show you for the rank of monomials, you don't have the power of the lowest exponent appearing. It's going to disappear in this way. Okay, but now what about Strassen conjecture? Well, so now we take two polynomials, say monomials. The red one, which is the one we just took, and the blue one, A0, A1, A2 are our new variables, independent set of variables. And now you compute the rank of the red one, we know is 12, and the rank of the blue one is 4. So if you take the sum of these two monomials, you get rank at most 16.
What's the degree of G?
Pardon me?
What's the degree of that?
Oh, sorry. That was a stupid mistake I made yesterday night. Yeah. So if you want to make this work, and I'm not trying to, I want to try to give you a nicer example if I make a stupid mistake. So this is the one we want to consider. So it's twice the same monomial, but simply with different variables. I forgot the exponent there, sorry. So what you get is at most 12 plus 12, 24. Yeah. So it's never a good idea to make last minute changes. Okay, just forget that, but you will see what is important about it in just a second. So what is important is that when you want to perform the game we played before, so you remember that ideal I before was just y0. Now is with two generators, y0 and b0. And then the linear form you pick here is y0 plus b0, which is a general linear form because you can rescale. No coefficients are important because you are in different set of variables. And now, if you compute, you get the right number, which is not 16, but is 24, as a lower bound. And so you manage to get that Strassen conjecture holds for the sum of these very two precise monomial. But you see that the upper bound, 24, is easy to get. It just comes from that formula. The lower bound comes from what? From the fact that you have a blue linear form and a red linear form, which are computing the rank. So this is the crucial part of it.
How do you know that's a general linear form?
Well, this is very easy from my point of view because just take 3y0 plus 4b0.
Okay.
And then you can just incorporate the coefficient. Because as they are in different set of variables, the coefficient can just be incorporated.
Yeah,
Why does it have to be a linear combination of y0 and b0 only? It could be, y0, y1, arbitrary.
But if you, I understand your question,
y0,
but
y1, y2.
In that idea.
exactly. So if you go back here, L is a general linear form in I. So you cannot use anything outside I.
Oh, you're only allowed linear forms in I. Yeah. Oh,
It's not,
I guess-
if you want to play this trick, yes, in the way we play it. If you want to play this trick in the way we play it, you only allow linear form in I. Yeah.
So you're saying that this statement here holds true for any I generated by linear forms?
This is what I have in mind. Yes, maybe you get a number which is too small. Of course, you have to avoid to take trivialities. But this is working because you basically, the more linear form you take, the less you take away.
So if you can take I generated by a single linear form?
Oh, yeah.
He did that right.
Yeah, this is the monomial case. This is the 2012 thing. If you want to compute this formula, you take one linear form. This is the example without the mistake, right? The mistake is the next example. But here you use y0. Yeah, you take one linear form and you perform it. And well, the one linear form case is the most natural, but the fact is that it's not always working. So if you play here with only one linear form at this level, you don't get 24. Say, we didn't manage to get 24 with just one linear form. And in many other examples I will show you, you need to play with the fact that I can have many generators, not only one. And then you must choose something inside I of degree 1. Yeah. Oh, sorry. Okay. So this is the example, and this is what is special about monomials is this fact here. So if you have this homogeneous polynomial, you say it is linearly computable. If you can find an ideal generated by linear forms, and when you compute this lower bound, it's equal to the actual value of the varying rank. So the special thing about these forms is that the rank can be computed in this way. And this is true, for example, for monomials, and this is relevant because this is what we realized, is that if you have this, then the property of coprime monomials of satisfying Strassen conjecture moves on. And it is satisfied from everything which is linearly computable. So if you have your homogeneous polynomials in different set of variables, and they are also linearly computable, then the rank of the sum is the sum of the ranks. So it's just not only for monomials, it's true for everything having the property of being linearly computable. So if you can compute the rank, if you can characterize the rank, it's not that you compute it, you characterize it in a nice way, so in precisely this nice way, then you can prove that the rank of the sum, when they are in different set of variables, is the sum of the ranks. So this is what the main thing I want to show you is this way of proving Strassen conjecture whenever you have these two properties, different set of variables and linearly computable. So now what I'm going to do is to show you some examples of linearly computable forms and some problems that arise when you want to work with them. So the first example is, well, this is just summarizing it. So the first example...
What's the simplest non-linear computable
Can you-
polynomial?
Oh, that's a good question. It's coming, well, I tell you, it's like this. Is the cubic, the first one I don't know how to compute linearly, is the cubic and a line and the tangent conic. So a irreducible cubic of this form is not
Can you just move
playing
back
this game.
one slide, please?
Can you move?
Backwards one slide.
Can you show
think
again
so.
the definition of linearly computable, please?
Yep. So linearly computable, you can find an ideal generated by linear forms such that for a general linear form there, you have these property. And if you want to show that something is not linearly computable, you need to know the rank, and you need to show that it's not possible to play this game.
Can I just understand the bound that you're having? So like if you take y cubed plus x cubed plus y cubed, just rank 2 polynomial, and then you take your ideal generated by dx. So what's your bound saying?
If you want, we can do that later. I don't want to enter in computation at this precise point. We can do that immediately after if you want.
Okay, that would be very good.
Yeah, perfect. I already made a mistake in one computation before. I don't want to make it two. If it is, first let's wait how many mistakes there are after this, and then we can do that.
I'm just trying to understand, and I think you lack assumptions in your lemma. The main lemma.
I know it's right, and maybe it's not rightly phrased here, but I don't think so. But we can just speak about that. So you worry about I, but I think it is what it is. It's generated by linear forms, yeah. And then you take the general one, but we can speak about it, yeah. So just to give the example of bimonomials again, so you have the rank. You can write this expression. You can easily find the upper bound as we did here, basically using the same trick. And the lower bound is coming, again, in the same way, using the lowest exponent variable. So you can do this, you find this complete intersection, and then you can multiply the degrees. Unless n is 0, you get this number. If n is 0, you get 1, just because your monomial is a power. So there is nothing to do, and the rank is 1. And so this is linearly computable in the simplest way. Other example of linearly computable forms are binary forms. And again, this is pretty easy. So the perp ideal has two generators, say degree d1 and degree d2. d1 is at most d2. And then we know there are two options here. If g1 is square free, the rank is exactly d1. If g1 is not square free, well, then the rank is d2. And if g1 is square free, then what you want to do is basically pick a linear form which is not dividing g1, and then you play this game, and the ideal you get is LG1, which is a complete intersection of degree d1. So in the red case, the rank is d1, and the rank computed in this way is d1, so it's linearly computable. And in the blue case, you have to play a little slightly different trick. You have just to choose L, which is a multiple factor of g1. If you do that, as soon as you have L, you also have g1, so what is left is g2, and this is the degree of what is left. So again, in this situation, you see what the problem is. The problem is that I'm able to show that it is linearly computable because I know the rank. So this is what I don't like up to this level. But I will hope to show you an example in which you can actually use this notion to discover what the rank is. So it's not too bad, but this is a problem. The problem would be to characterize linearly computable form without the need of knowing the rank, because knowing the rank is difficult. And then there are more examples. So for example, always this reducible form we saw before, and they are linearly computable, and also the one in which you add the power is linearly computable, and then also the one with only 3 variables, now no restriction on the fact that A must be large enough, and again adding a variable. And then there is van der Molen determinant, misspelled, second mistake. So they are linearly computable again, and I think this is coming from your paper with your I guess. It's inside there. I got it from there, so I just made a computation, but it's coming from that. And then also this big family, which again is coming from something I read in your paper, and then my explained to me, is that if you have G, and you know that the perp ideal of G is a complete intersection, maybe you don't know what the rank of G is, But if you multiply g by a linear form, which is a new variable, say, a new variable, then the form you construct in this way, you can compute the rank of it, and you know it is linearly computable. And so, for example, families of G such that it is a complete intersection, I think they are this Q fundamental invariant of reflection group of hyperplane arrangement. So there is a big family of polynomials of which you can you can use to construct the example by multiplication. Okay, and after this, there are several questions. So all the examples I show you are showing you that are of reducible forms. So the question could be, well, maybe all linearly computable forms are reducible. And this is not true. And one example is the nodal cubic. So the nodal cubic is linearly computable, but is not reducible. So it's not true that linearly computable means reducible. And also the converse is not true. So is it true that reducible forms are linearly computable? I don't know, but I doubt it's true. And for example, the easiest example is this reducible cubic. So a line with a conic to which the line is tangent is reducible, but we don't think it is linearly computable. So
You know there exists polynomials that are not linearly computable, say by dimension calculus.
I don't try really hard, but I think that I show you one way now.
Well, the general cubic, I think, because the polar ring is too small, no, to get.
Very likely you have many examples, but I was looking for an example who was easily explained in some sense. And there is some geometry explaining it. For example, the smallest one, which I think we can show is not linearly computable, so is the following. So if you take anything like this, so say x0, and then you have, say, x1, so it's again this kind of game. So this A, and then you have B powers. And if you look at this one, we know that when A plus 1 is more than B, we know what to do. So if A plus 1 is less than B, maybe this is something we don't know how to do explicitly, but we discovered that we can do this. So we can compute the rank of this one, and this is basically 3B. Okay, so for example, the smallest one we can consider is this one. So x0 and x1 cube, x2 cube, plus x3 cube, something like this. And then these you can show the rank is 9. But the fact is that if you use the lower bound I show you, both of them, what you get is not 9. The best you can get is 8. So in this situation, for this f, the rank of f we know is 9, and these elementary techniques only produce that the lower bound is 8. So basically, using those techniques, we know that is at most 9, we know is at least 8. To show that this formula holds, to show that it is actually 9, we need to play a little bit more with this ideal, with this f perp colon I plus L. And basically, it's not just looking at the dimension at the Hilbert function. You have to look more carefully to what would mean to have rank 8. So it will give you some equality between ideals. So you get some nice property, and you can show that, well, 8 is not possible. And the same trick carries on here to show that it is 3B. And this one is another example in which I'm pretty convinced we can show is not linearly computable. And the idea why this is not linearly computable is kind of nice. And the fact is that you can, so you have that polynomial there, and we know the rank is 9. So there is some apolar ideal, so some scheme, zero-dimensional scheme of 9 points sitting there. And the fact that is that you can always find some of this scheme with a very nice shape, which means that you have the 3 lines, so say x1 equal x2 equals 0, and x1 equal x3 equals 0, and x2 equal x3 equals 0. So among all these schemes of 9 points having this property, there are some like this. So nicely organized. 3 lines, and on each line you have 3. And the fact is that you can move the points back and forth. So basically each point of this line will be a point of an apolar subscheme of 9 points. So a scheme you can use to decompose F. And now if you pick your L in any way, you can move these points in such a way that L will contain at least one. So this is the plane L equals 0. It will contain one of these points. So basically, if you use I equal the ideal of L, when you compute that column ideal, you lower the rank. So the best lower rank you can get using our technique is 8. So this is why I believe, refining this argument, you can show that this form is not linearly computable. And the geometric reason is that pick your L, I can move the points, they are still apolar, one point is going to be deleted. And when you play that game, you cannot exceed the cardinality of this set of points, so you can always get at most 8, but the rank is 9, so you cannot compute the rank, and the form is not linearly computable. So this is just one example about this. And I think that we are almost over. Yep. Okay, so thank you.
Okay, further questions for Enrico?
Is that statement, known for, the symmetric, right, called, Warring rank? Is that conjecture known for border rank, symmetric border rank, Warring border rank?
You mean the Strassen part?
Yeah.
I don't know about that actually, but I don't think so.
So it's not known to be false for us.
It's not known to be false. No, that's I'm pretty sure. It's not known to be false. Yeah.
Techniques can be used to prove or disprove common conjecture.
You mean using these for tensors which are not symmetric and
Yes, and to prove better lower bound to disprove common conjecture.
Oh, I think we never tried about it. I don't know. Actually, I never thought about that. About going back to tensors. No, I don't know. Yeah. This is very special about polynomials because you play with a lot of this commutative algebra, which is special of homogeneous forms.
Any further questions?
Yes. Yeah, so this is for the complex rank, right?
Yeah.
What happens in the real rank case?
It was my question also, exactly the same.
Okay, I have a very easy answer, which is I have no idea because I never considered that. Yeah. So this just play with the complex numbers. Yeah, everything is there because it's easier for us. I don't say it's needed, but this is what we are using.
Do we know whether it's much different from the ones in the computer?
I
or
don't.
For monomials, let's say.
But for monomials, I know a little bit in the binary case is different. So if you have monomials in 2 variables, the real rank can be larger, and we know exactly how large is the sum of the exponent rather than the largest plus 1. But if you have more than 2 variables, I have no idea, even for monomials. And what I can tell you is that when you compute for monomials this expression, usually you have a lot of complex coefficient appearing. So I would expect that it's going to be larger, but I cannot tell you how larger it's going to be. For 2 variables, we know because it's very easy, but just 3, I don't think is known.
Do you know if it's true for border rank, the results that you have for linearly computable?
Actually, I don't know. Maybe Luca was thinking about it, but I don't know.
Not in that extent. In special cases, you can probably use some kind of trick, but not that one. If I can add one comment, is that of course you can strengthen the conjecture saying except for trivialities, you may ask if all possible decompositions come from the decomposition of F and decomposition of G, which is stronger. And in that case, probably you need some new idea because the reduction that you get is not, maybe that you don't get all possible decompositions. So a clear insight of all possible decompositions. So there is still a lot of space to be explored.
Okay. Yes, Bernard?
So the same question could be asked for cactus rank?
Oh yeah. But the answer is the same, which I don't know. I know it's boring, but...
What was Bernard's question?
cactus rank.
Cactus rank instead of Waring and...
I mean, the monomials, your lower bound equals the Waring rank, and the cactus rank and border rank are smaller, so this is not a lower bound for those cactus and border rank.
No, I think the question is if a cactus rank is additive.
Yeah. Strassen conjecture for cactus rank, yeah, well, sure.
So for monomials, we know that
It's not. Your statement proving that it's not.
Okay, well, there are a lot of great questions, and before we break, I want to remind you of something you may have gotten on an email. No. So there's a website for where you can post these kind of questions that you're asking that no one knows the answer to yet. So here's the website, www.ocf.berkeley.edu. And then Drew Mason. Slash one more thing. Okay, so here's the idea. So there have been many great open questions presented, and the last time I mentioned this at a previous conference, I said, if you have a very large box that has a computer in it, and you could ask it one question, what question would you ask? So that's problem type number one. For instance, what's the S rank of 2 by 2 matrix multiplication? That's on the list. And then the lower on the wiki is general open questions if you would like to submit an open question which is not computable by a large computer. And if you're really afraid of wikis, you can feel free to just email me your question and I will be very happy to post it to the wiki. But I would be very happy if you guys can help contribute to the list of open problems related to this workshop. So thanks. And then we'll meet back again at 3:50. Thank you, Enrico.